This is Mr. T's commentary video over chemical reactions and conversions, part 1. So we're going to be exploring how to use chemical equalities in order to do chemical conversions. Here is the outline. So first we're going to be understanding moles, which is a collection unit, and then we'll be doing conversions with moles. Moles to atoms. We'll be getting into moles to grams using molar mass, and then doing more complicated ones going from grams to moles and moles to atoms. So let's go ahead and start off. We have something called collection terms. We've already been studying these in our chapter 1-2 slides. We just didn't realize it. So a collection term, for example, would be dozen or ream or case. It's some sort of group number. And then we make an equality based on the collection term from that group number, such as dozen, to the number of units. So 1 dozen donuts is for 12 donuts. Now the collection term can be used for anything. So 1 dozen eggs can be 12 eggs. 1 dozen pencils can be 12 pencils. What we're going to be using in chemistry land is the collection term mole. So 1 mole of a substance is equal to 6.02 times 10 to the 23rd atoms. That is not a typo. That is over 20 zeros added to this number, which is amazing. So this is our favorite chemistry collection term that we're going to be using. Cool thing is that this number never ever changes. Furthermore, we can assume that any element found on the periodic table, we can always assume that 1 mole of that element will always be this number right here, 6.02 times 10 to the 23rd. The fancy name for that number is called Avogadro's number. So make sure you know that. We can also assume that 1 mole of any substance, even if they're molecules or formula units, so molecular formula, ionic formula, 1 mole of any substance will always be 6.02 times 10 to the 23rd. And it's written in this equality format, which allows us to do conversions. So here is our equality, and then here is the conversion factors. And this was one of the main reasons why we learned how to do all of those conversion factor calculations in chapter 1 and 2. It is because we use that same math format to do conversions with moles and Avogadro number. So let's go ahead and see this in action. How many copper atoms, there's the number, are in 0.50 moles of copper? So here is my starting value. My original equality, and I'll just write it above here, was 1 mole of copper equals 6.02 times 10 to the 23rd copper atoms. So there's my collection term right here, and then here is the number. I need to go ahead and put moles on bottom when I convert it into a conversion factor in the equation. So moles goes on bottom, and then atoms goes on top. You'll notice the moles cancel out, and then this allows us to do our calculation. Please keep in mind you have to be really good with scientific notation on your calculator. So make sure you know how to plug it in. For example, every calculator has either an EXP or an EE function. which means times 10. You cannot simply type in times 10. It won't work right. You'll get the wrong answer. So here is the final answer. And this should make sense. If we have 1/2 a mole, then we should have 1/2 of Avogadro's number. So it's 3.0 times 10 to the 23rd. The next thing, we can always assume, just to make our lives easier, that the starting value will always be measured with 2 sig figs, and Avogadro's number will always be measured. In this case, it's going to be 3 sig figs. Because it's a measured value, different instruments have a different number of sig figs. So some books will have 6.022, other ones will have 6.0223. I'm always going to use this one right here, 6.02. So we have 2 sig figs, 3 sig figs, so it's rounded to 2 sig figs. Here is another problem, only this time we're starting with molecules. So you'll notice the equality never changes. So 1 mole is equal to 6.02 times 10 to the 23rd, and then we simply put in the name of the substance. 1 mole is CO2, 6.02 molecules of CO2. The molecules has to be such that they cross cancel, so that's why molecules is on bottom and moles is on top. And then there is our final answer. Starting value has 3 sig figs, and then 3 sig figs in our conversion factor, so therefore the final answer should be rounded to 3 sig figs. So more examples for you to go through. So we just explained how to do moles and moles to number of atoms and number of atoms to moles. Now we're going to be getting into what I think is a bit conceptually tricky. Moles of atoms within moles of the molecule. So for example, here I have a molecule of H2O and there's 1 mole of it. It turns out that if we simply look at the subscript 2, it's automatically implied that that 2 means that there's going to be 2 moles of hydrogen. Going back to the slides. Slide 9. Let's go ahead and show you my Lego block example. My son likes making Lego blocks. So this is supposed to be a kangaroo. Just go with it. Notice the kangaroo is made up of 2 red blocks and 1 purple block. Now we can assume that if we had 1 mole of it, then we have 1 mole of the purple blocks that help make up the Lego kangaroo, and we have 2 moles of the red blocks. So these are the number of individual blocks within the main Lego kangaroo, so to speak. So using that analogy, here is glucose. Glucose is made up of 6 carbon atoms within that molecule. So think of those as building blocks. And then H has 12 atoms that make up that portion of the molecule. And then here we have oxygen O, which has 6 atoms that make it up. So in short, for 1 mole of glucose, we have this ratio of 6 carbons, 12 hydrogens, and 6 oxygens. We can automatically assume that it's a mole-to-mole ratio. So for every 1 mole of glucose, we're going to have 6 moles of carbon, and then 12 moles of hydrogen, and then 6 moles of oxygen. So there's our ratio. Now, what you're going to be asked to do is go ahead and make an equality based on the glucose molecule. So for example, I could say something like this. 1 mole of C6H12O6 is equal to 6 moles of carbon. So how would I use this? You could have a question like this, where it says, given 3.0 moles of C6H12O6, how many moles of carbon are present? And we'll usually say something like this, moles of carbon atoms. Moles of carbon atoms. So I really should say that because it's the number of atoms within the molecule. So let's go ahead and set up our problem. We have our starting value, 3.0 moles of C6H12O6. We have our conversion factor. Moles of the C6H12O6, or glucose, go on the bottom because that way it cross cancels. And then we have 6 moles of our carbon atoms. And so it cross cancels out, and then our final answer is going to be 18 moles of carbon atoms. Now, starting value is always measured, so in this case 3.0 is 2 sig figs. Ratios are non-measured. So think of them as having infinite sig figs, so in this case we just have to go by the starting value with 2 sig figs. Now, if I wanted to, I could take this question to the next level. So, given 3.0 moles of C6H12O6, I could say how many number, keyword is number, of carbon atoms. So we already know that there is going to be 18 moles of carbon atoms, but now we need the number, so we have to use Avogadro's number. So 1 mole of carbon atoms is going to be equal to 6.02 times 10 to the 23rd carbon atoms. So using my calculator, the answer is 1.1 times 10 to the 23rd carbon atoms. So I broke this up into 2 separate calculations. You can do it that way, or you can just write it as one main calculation. So that was glucose, This right here is aspirin. And again, we can go ahead and break it up into moles of our aspirin. Let's do another one. So how many moles of oxygen are in 0.150 mole of aspirin? So in this case, I have 0.150 mole of C9H8O4. Setting up my conversion factor. 1 mole of C9H8O4 is equal to, let's see, we want oxygen. So it's going to be 4 moles of oxygen atoms. The 1 mole of C9H8O4 goes on bottom. The 4 moles of oxygen atoms goes on top. And then that would lead to 0.600 moles of C9H8O4. Now, the next one is how many oxygen atoms. And it's implied that it's how many number of oxygen atoms are required. So, in this case, it would be C9H8O4. And I'm just going to do this as a 2-unit conversion so you can see it worked out. And it's all nice and neat. The problem starts off the same. And we're converting to moles of oxygen atoms. Only now we're going to go one step further. We know that 1 mole of oxygen atoms is equal to 6.02 times 10 to the 23rd oxygen atoms. So the 1 mole of oxygen atoms goes on the bottom. And then the 6.02 times 10 to the 23rd oxygen atoms goes on top. We then go ahead and do the calculation. And we have an answer of 3.61 times 10 to the 23rd. And that's the number of oxygen atoms. Starting value has 3 sig figs, and then Avogadro's number has 3 sig figs. And then the ratio of molecule to atoms, we ignore that. So you want to go ahead and practice these, and we call these type of problems the moles or number of atoms within a molecule. Now we're going to move on to the next part, and we're going to get into calculating molar mass. Here's the periodic table. You learned that that bottom number I call atomic mass. And the purpose of atomic mass is it's a weighted average, allowing us to ignore variations in isotopic masses. So this weighted average right here for the atomic mass allows us to ignore the different types of isotope masses. It makes all the calculations very nice and neat. Now, we have another term for the atomic mass. We also call it a molar mass. A molar mass. So if we were to sit there and measure out 1 mole of any substance, and it doesn't matter what it is, it can be any substance on the periodic table, such as carbon, and put it on a mass balance, whatever that weight right there, we call the molar masses. And the name should speak for itself. Molar refers to mole, and that's the mass for 1 mole of that substance. And it's 12.01 grams. Please keep in mind, though, that every periodic table has used different balances, so therefore their numbers are going to be slightly different depending on the accuracy of the mass balance. So in this case, that mass is from a really high-end mass balance, so 12.011. So this will be important later on because I'll have to specify which periodic table to use when we start accounting for sig figs. However, you can assume that atomic mass is the same thing as molar mass. And if we assume that regardless of what element we're looking at, if we take 1 mole of it on a mass balance, then that's the number down below. So 1 mole of chlorine is going to be 35.45 grams, for example. 1 mole of cobalt is going to be 58.933 grams. Again, the numbers may vary slightly depending on what periodic table you use because they use different balances with different number of sig figs. So this specific periodic table, it didn't have as accurate as the previous periodic table's balances. So that's why there's less sig figs. That one only went to 12.01. Alright, so that's pretty straightforward. Let's go ahead and make it a little bit more complicated. You could be asked to figure out the molar mass of a molecule or a formula unit. So molecules such as H2O or a formula unit, that basically refers to anything that's an ionic compound, such as sodium chloride. Now, just to make the math a little bit easier so we can understand the concept, we're going to use Mr. T's cheap periodic table. So 1 mole of hydrogen is going to be 1.0 grams. 1 mole of oxygen is going to be 16.0 grams. So we need to go ahead and find the molar mass for H2O. Now this is pretty straightforward. All we have to do is add up the molar masses of each of the individual atoms, and we have the molar mass of the molecule. So in this case, for hydrogen, it's going to be 1.0 grams, 1.0 grams, 16.0 grams. And so the molar mass for H2O is going to be 18.0 grams. We can do the same thing with sodium chloride. There's sodium, there's chloride. So I've added the equalities in the upper right hand corner. So 1 mole of sodium is 23 grams, 1 mole of chlorine is 35 grams. Here's the sodium, here's the chlorine, and then we have 58 grams. Now that's using my cheap periodic table, and I use that because it cut down the math. On the left hand side we had 1 decimal place for each of those. So the least decimal places, when we add it together, is going to have 1 decimal place. Whereas over here, we had no decimal places, so the final answer should be rounded to no decimal place for the molar mass of NaCl. Now, I could give you harder problems where you have to use the periodic table. So going back to our periodic table, sodium is 22.990 and then chloride is 35.45. So you'll notice there's a lot more values, and you have to account for sig figs if you're adding them together. So here we have 2 decimal places, here you have 3 decimal places, and so it should be rounded to 2 decimal places. My last comment is oftentimes when we write molar masses, sometimes we'll write it in a condensed format. So for NaCl, it may be written like this: 58.44 grams per mole, like this. And then it's automatically applied that that is the molar mass. This makes it pretty easy because then you just simply have to bring to the other side of the equal sign the 1 mole, and we can go back to our original equality. 1 mole is equal to 58.44 grams. Now I'll specify which periodic table to use, and sometimes just to cut down the amount of math you have to do because that takes up time, I'll make it really easy for you. Other times I may want you to use a periodic table and you'll need to use that extra time to come up with the proper molar mass. Now these are some pretty simple molecular and ionic formulas that I gave you. I could make it more complicated. Oops. I could make it a little bit more complicated and give you one such as calcium chloride or potassium phosphate. So here's calcium chloride. So this is the table method in order to calculate the molar mass. And you might think of doing this when you're dealing with bigger molecules. Now you could still use the original method where you just simply tally the calcium and chlorides and add them all together. That could give you the same answer. But I want to expose this one to you. So in this case, we go ahead and we create a table. We have the element, number of moles of each, the atomic mass, and then the total masses for each element. And these are subtotals that you'll then add together. So because there's only 1 calcium, then you put a 1 here, and then you put the atomic mass from the desired periodic table. You then go ahead and multiply 1 times this atomic mass. It's multiplication, so least sig fig rules, so 3 sig figs, 3 sig figs. Because there's 2 chlorine here, you put in 2 here. So 2 times 35.5, that gives you 71.0. Again, obeying the sig fig rules, 3 sig figs here, so that should be 3 sig figs. You then add it together, and then that gives you the molar mass for this species right here, calcium chloride. And then when you add it together, it's least decimal places, so 1, 1, and 1. Now, it might have been easier just to go ahead and then put in the individual molar masses like this and add them together and go by these decimal places. But it's much harder if you have a problem like this, where there's multiple ones, and that would take forever just to add in a serial fashion. So let's do potassium phosphate. There's 3 here, 1 phosphorus, 4 oxygen. You then put in the atomic masses, and they're all measured, so 3 sig figs, 3 sig figs, 3 sig figs. We don't look at the sig figs for the number of moles. That's considered non-measured. So 3 times 39.1. Here's your intermediate value. 1 times 31.0, intermediate value, and then one more intermediate value for 64.0 from 16.0. That's a lot of words. So let's go into the sig figs. First off, there is a mistake in this slide. if I multiply 39.1 times 3, then I actually should have just had 117, because we're doing multiplication as least sig fig rules. Consequently, well, my final answer should actually be 212 grams. So you can tell that as the molecule gets bigger, or in this case the formula unit gets bigger, then it's very easy to get tripped up on sig figs. So please be careful. So that's 212 grams. So this is pretty cool. This shows you how big each substance is inside a beaker. If we measured out exactly 6.02 times 10 to the 23rd, notice they all have different sizes. And then when we put them on the balance, these are each of the molar masses. I thought that was kind of cool. So you can use that table method, or you can just use an equation method and just work it out this way. But please be careful of your, please be mindful of your sig fig rules. Now, let's go ahead and do a giant one. Again, it's easier to multiply each element, the number of each element, by the molar mass. Trying to list them all in a nice serial fashion where you just add everything together, that would be crazy. Once we've learned how to create a molar mass from our desired molecular or ionic formula, we then get to go ahead and use it as a conversion factor. So now we're going to start going back into conversion factors. So this is acetic acid, C2H4O2. It's found in vinegar. It's what makes vinegar vinegar. So here is the molar mass that we calculated out using acetic acid. And this is from a pretty cheap periodic table, which is why the numbers are so small. And we can write it one of two ways, depending on how it cross-cancels in an actual problem. So using the molar mass as a conversion factor, we're able to go from grams to moles and moles to grams. So let's see this in action. How many grams of aluminum are in 3 moles of aluminum? So in this case, I'm starting off with 3 moles of aluminum. Starting value is always measured. There's 3 sig figs. And then I'm going to go ahead and turn my molar mass equality into a conversion factor. Notice the moles, the 1 mole of aluminum has to go on bottom, so that way it cross-cancels, leaving grams on top. So by using the periodic table to calculate the molar mass, or just simply writing it down if it's an element, we can create these molar mass conversion factors. And so we can convert from moles to grams or grams to moles. And this should make sense, relative sense. If I had 1 mole, which was 27 grams, then having 3 times the amount, or 3 moles, then that should be 3 times the amount of the 27 grams, giving a total of 81 grams. And we can do this for much bigger molecules. Once we figure out the molar mass, we can use it as a conversion factor. In this case, we had to invert it or put the grams on the bottom, because that way the starting value grams cross cancels, and that leaves the desired moles. Now we're going to be going into a little bit more. Here is the outline. You should already have understood and able to calculate molar masses. That's very important. And know how to go from simple moles to grams and grams to moles. That's also important. And in the last part, we're going to be combining grams to moles and moles to atoms. Moles to the number of atoms. So it'll be grams to moles to number of atoms. Usually these are going to be at least 2 conversion factors that are going to be required. It could be 3 if we're counting the number of atoms within a mole of a molecule, for example. But for right now, we'll start off with 2 conversion factors. So, starting off with grams, we could go from grams to moles using the molar mass as a conversion factor, and then moles to particles using Avogadro's number as a conversion factor. Conversely, we can start off with particles using Avogadro's number to convert to moles, and then using molar mass to convert to grams. So let's see this in action. How many water molecules are in 24.0 grams? So I'm going to need to go from grams to moles, and moles to molecules. Now you just can't transfer directly from grams to molecules. You need the moles. So moles is an important middle step. Always, always, always. So a starting value is always measured, 3 sig figs. We need to go ahead and use our equality. So that means you have to calculate the molar mass of water, and you should on your own be able to calculate out 1 mole of H2O equals 18.0 grams of H2O. And you should already have memorized that 1 mole of any substance is always going to be the number 6.02 times 10 to the 23rd. So grams goes on bottom because it cross cancels. It's measured, so there's 3 sig figs on that one. Now we need to go ahead and put in the Avogadro's conversion factor. Moles goes on bottom because it cross cancels, leaving Avogadro's number 6.02 on top with 3 sig figs. So the least sig figs is 3, so it's going to be rounded to 3 sig figs. When I did the calculation on my calculator, I did times, divide, times, and divide. But every calculator is different, so you want to practice doing these so you can master it. Just not only to master the concept, but also to master your calculator. Nothing's worse than getting a wrong answer on a quiz or exam because you didn't use your calculator properly. Again, be aware of how to use the EE or EXP on your, or times 10 if there is a special notation on there for your calculator in order to put it in properly. So last example, in this case, we're going to be going from grams to moles and moles to molecules. So we start off with grams right here with 1 sig fig. We then use molar mass, so we have to calculate out. And that was from a cheap periodic table because it only goes to 1 decimal place. And then we use Avogadro's number and a conversion factor. And moles has to go on bottom so it cross cancels. Leaving our final answer. So 1 sig fig, 4 sig figs, 3 sig figs. So the lowest one is going to be 1 sig fig. So it's rounded to 1 times 10 to the -9th. So be sure to practice these problems.